So this is the overview for the topics which we're gonna cover under this particular video. All the number system, binary number system, decimal number system, octa number system, hexa number system, and the conversion between each of this number system, like binary to decimal, decimal to binary, binary to octa, and vice versa. Nearly we will be having 12 conversation between the 4 number systems. Then what are ones complement, what are twos complement, and using ones complement and twos complement, how the subtractions are done, and then the binary arithmetic. Addition, subtraction, multiplication, and division. Okay, before we go what exactly binaries are, what exactly digital are, let's have a little comparison between analog and digital. So how the analog signals are, they are continuous, infinite range of values, more exact values, but more difficult to work with. Whereas if you see the digital signal, they are discrete in nature, finite range of values, not as exact as analog, but easier to work with. We have given an examples also here. Now you can see that the analog watch as well as the digital watch, the advantage is battery life, programmability, and the accuracy will be more in the case of digital system. The world itself is analog. Example, if you see the example, sounds are analog signals, they are continuous time and continuous value. Our ears listen to analog signals and we speak with analog signals. Images, pictures, video are all analog at the source, and our eyes are analog senses. Measuring our heartbeat, tracking our activity, all requires processing analog sensor information. If you see the example, an analog signal can be any time varying signal. Minimum and maximum values can be either positive or negative. They can be periodic or non-periodic. Sine waves and square waves are two common analog signals. Video and audio. Now you can see here, this is a sine wave. It can be periodic or non-periodic. We have taken a square wave and the random periodic wave. What are the parts of the analog signal? If you see that this is an amplitude. Amplitude is nothing but maximum distance traveled by a particle. So this will be the maximum distance. So this is called as an amplitude or peak. Time period, time taken for one complete oscillation. So it means from here until the time it have taken to complete here. So 360 degree. So this is a time period, and frequency is nothing but number of oscillations per second. So we can see that this is peak to peak amplitude. This is in one direction amplitude. This is a time period, and these are the frequency. What are pros and cons of analog signal? Let us see first the advantages. Major advantages of the analog signal is finite amount of data. Density is much higher and it is very easy processing. But there are disadvantages which are nothing but unwanted noise in recording. If we transmit data at long distance, then unwanted disturbance is there. Generation loss is also a big drawback of analog signals. Logic levels. Logic level is a voltage level that represents a defined digital state. What is that? It can be high or it can be low. So logic high is the higher of the two voltages, typically 5 volt. Normally we consider 5 volt. And low voltage is nothing but which is a 0 volt. Now here you can see that, see, this is a logic level. High in the sense it is a 5 voltage, low in the sense it is a 0 voltage. And because it is in high, we can say it is a true. Low, you can say it is a false. Or because it is in high, we can call it as an on. For the low, it can be called as an off. Or in the state of binary, we can say that because it is in high, so this is 1, and low, this is 0. So these are the two only logic levels. It can be 0 or it can be 1. So now you can see that this is a logic level with a 0 voltage and logic high with a 5 voltage. Now examples of the digital signal. Digital signals are commonly referred to as square waves or clock signals. Their minimum value must be 0 volts and their maximum value be 5 voltage. They can be periodic or non-periodic. The time the signal is high can vary anywhere from 1% of the periodic to 99% of the period. And it can be text or integers. So now you can see here the different kinds of digital signals. We have taken a square wave. So this is a 0 and maximum is the high. So this is periodic, or we can take it as a non-periodic also. So these are the example of the digital signal. Now, what are the parts of the digital signal as we have seen in the case of analog? So here again, the maximum distance traveled by a particle is nothing but an amplitude. Okay. Time taken for one complete oscillation is nothing but a time period. This one is the time period. And the frequency is number of oscillations. 1 by t is nothing but in hertz. The number of oscillations per second is called as in frequency. Time high. So here, see, this I have taken a time high. The signal is at 5 voltage. So this is called as a time high. Okay. And what is time low? The time the signal is at 0 voltage. So this is nothing over there. So this can be called as in 0 voltage. And from here to here, we have a signal. So this is called as in 5 voltage. So this is time high and this is time low. What is rising edge? From 0 to 1. Transition of the signal is called rising edge. Falling edge will be from, this is 1, right? This is 1 and this is 0. So from 1 to 0 is called a transition of the signal, or it can be called as a falling edge. What are the advantages and disadvantages of the digital signals? Because of their digital nature, they can travel faster in our digital lines. Ability to transfer more data as compared to analog. And drawbacks are greater bandwidth is essential. Systems and processing is more complex in the case of digital signal. If you see this, an example using a digital over an analog. So this is an analog signal, a noisy channel. So you can see that the signal plus noise. You can very clearly see that there is a signal, but it includes a noise. Whereas if you see a digital, so digital systems are less sensitive to noise. You can see here, very less sensitive to the noise. As long as 0 is distinguishable from 1. So this is clearly shows that why we should go for a digital, because in the case of analog, the noise is clearly shown over here, but whereas in the case of digital, it is less sensitive to noise. Analog system, the physical quantities or signals may vary continuously over a specified range. Whereas in the case of digital system, the physical quantities or signals can assume only discrete values with a greater accuracy. You can clearly see that this is analog signal and this is a digital signal. Few more points for the advantages of digital over the analog system. Digital systems are easier to design. Information storage is very easy. Accuracy and precision are greater. Digital systems are more versatile. Digital circuits are less affected by noise. More digital circuitry can be fabricated on integrated chips. Reliability is more. So these are the many advantages of digital system over the analog. Basically, how you will define a signal. A signal is a physical quantity. It can be sound, light, voltage, current that carries information, isn't it? The power cable supplies power but no information. A USB cable carries information. Normally, for the exchange of data from our mobile phone to laptop or vice versa, we use a USB cable which carries the information. Examples of quantities used as digital information signals. Now, for the voltage, 5 volt is logic 1 and 0 voltage is logic 0 in digital circuits. Magnetic field orientation in magnetic hard disk. Pits and lines on the CD surface reflect the light from the laser differently, and that difference is encoded as binary data. This was all about the differences between analog and digital, why we should switch over to the digital, what are the advantages and pros and cons of the analog as well as the digital. Now we will study the number system. Basically, what is a number system? A number system defines a set of values used to represent a quantity. To address that particular quantity, we should define it. So we should define with a set of values. So we can say that a number system defines a set of values used to represent quantity. Now we have all these four kind of a number system. We will have an exclusively topics covering onto the each of the number system. The first is called as a decimal number system, and whose base, or it can be called as a radix, is of 10. We'll understand how the 10 comes over there. For the binary number system, the base is 2, or it can be called as a radix 2. For the octal number system, the base is 8 or radix 8. For hexadecimal number system, the base or radix is 16. Okay. Now let us understand the first number system called as a decimal number system. This one, which is having a base how much? It is having a base of 10. So decimal number system contains 10 unique symbols. And what are they? It is from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So if you club all together, these are how much? These are 10 numbers. Since counting in decimal involves 10 symbols, we can say that its base or radix is 10. That's how the base is categorized. The total number of this particular number system is nothing but it's a base, or it's called as a radix. So because if we count from 0 to 9, the total number are 10. So for the decimal number system, the base is 10. It is a positional weighted system. See, in this system, any number, it can be integer or fraction or mixed, of any magnitude can be represented by the use of these 10 symbols. Each symbol in the number is called a digit. Each symbol in the number is called a digit. Like what we say, it is 0, 1, 2, 3, 4 and so on forth. So 0 is a digit, 1 is a digit, 2 is a digit. So each symbol in the number is called a digit. If you see the structure, this is a decimal point. This is decimal numbers, okay? So this is a decimal point. And for this particular numbers, what is the positional weights? So right from here, this is a decimal point. So this will be D0, D1, D2, D3. And here this will be D-1, D-2, D-3 and so on and so forth. So this is least significant digit and this is most significant digit. So how it comes, the positional weights will be, because the decimal number system have the base of 10. So this comes like 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. And here 10 to the power of -1, 10 to the power of -2. For the least significant digit, 10 to the power of -1, 10 to the power of -2, 10 to the power of -3. And for the most significant digit, from left to right, it will be 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. That will be the positional weights of a decimal number system. What is MSD? The leftmost digit in any number representation which has the greatest positional weight out of all the digits present in that number is called most significant digit. So this we can say that this is the most significant digit, and this we can say that this is the least significant digit. The rightmost digit in any number representation which has the least positional weight out of all the digits present in that number is called least significant digit. So further we will be saying that it is an MSD and LSD, or MSB, LSB for the in the case of bits. These are the basic number system example. Any number, it is a mixed fraction or an integer. Binary number system is a positional weight system. That was a decimal number system. Now we are studying about the binary number system. So the binary number system is a positional weighted system. It contains two unique symbols, 0 and 1. So how many total numbers we have in the case of binary? We have only two symbols. What is that? 0 and 1. Because we have only two symbols, what are the total numbers in the binary number system? We have 2. So what will be the base or radix? It will be 2. Since counting in binary involves two symbols, we can say that its base or radix is 2. A binary digit is called a bit. So each number, like in the case of binary number system, we have only two digits. What are they? One is 0, the other is 1. So that each individual digit is called as a bit. So now a binary number consists of a sequence of bits, each of which is either 0 or 1, because only two numbers are existing in the binary number system. The binary points separate the integer and the fraction parts. So now we can say that this 0 is 1 bit. This 1 is 1 bit. Let's understand the structure of the binary number system. This is the binary point, that was a decimal point, and this is the binary point. Okay. If you go back and see here, see, this is a decimal point because this is a decimal number system. So this is the decimal point. Now if you come back to here, this is a binary number system and this is called as a binary point. So as usual, this will be least significant bit, because here we are saying that each digit is called as a bit. So that's the reason we have labeled this as an LSB. And for this side, this is the largest number. So this is called as the most significant bit. So B3 here, we can say that the most significant bit, and B minus 2 is called as the least significant bit. And from the binary point, this will be, because binary numbers have only two numbers. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and here 2 to the power of minus 1, 2 to the power of minus 2. So this will be the positional weights of that particular binary numbers. The leftmost bit in a given binary number with the highest positional weight is called most significant bit. We already studied this. The rightmost bit in a given binary number with the lowest positional weight is called least significant bit. LSB and MSB. Now we have few of the decimal number systems and binary number system. Now you can see that these are decimal number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and up to the 15 number. Okay, this is the normal decimal numbers. Now what are the binary number? It is 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and for the 15th decimal number, it is 1, 1, 1, 1. A simple trick is, always remember that for 7 decimal number, it is 3 ones, 0, 1, 1, 1, and for 15, it is 4 ones, 1, 1, 1, 1. We will see how the conversion takes place between the decimal and binary into the decimal into the next slides. We said that each digit in the binary number system is called one bit. So the binary digits 0 and 1 are called bits. Single unit in binary digit is called bit. It means this 1 is bit, the 0 is bit. Now, what is nibble? A nibble is a combination of 4 binary bits. Like you have, this is one binary bit. So if you have 4, like 1 1 1 1 or 1 0 1 0, whatever the number we take it. So like example, like 1 1 1 0. So how many bits you have? You have 4 bits, 1 and 2 3 4. So this 4 bits is called a one nibble. A nibble is a combination of 4 binary bits. So this is called one nibble. This is one nibble, one nibble. Any number it can be. What is byte? A byte is a combination of 8 binary bits. It means 2 nibbles, because one nibble have 4 bits. So 8 bits is nothing but 1 byte or 2 nibbles. The number of distinct values represented by a byte is 256, ranging from 0000, 0000 to 1111, 1111. So this is how it is represented by the byte of 256, ranging from this to this value to this value. So here we can see that we are having 8 binary bits. This is 8 binary bits, isn't it? And here we can say that this is the lowest significant bit and this is the most significant bit. So we have 4 bits is called one nibble. So lower order nibble, and this is called higher order nibble. What is word? We hardly use this word. Normally we say that bits or bytes. Normally we don't use nibble also. And a word we hardly use this. A word is a combination of 16 binary bits. Like 8 bits is called 1 byte. So 2 bytes will be nothing but what? 16 binary bits. So this is called as a word. A word is a combination of 16 binary bits. Hence it consists of 2 bytes. Now you can see that this is the least significant bit at the last side, and this is called most significant bit. So this is 0 to 7 will give 8, and from 8 to 15 it will give more 8. So 16 bits is called a one word. Double word is nothing but a double word is exactly what its name implies, 2 words. It means 32 binary bits is called a double word. Now let us understand. We have understood what is decimal number system. Next, what are binary number system, and the third is octal number system. So octal number system is a positional weighted system. It contains 8 unique symbols: 0, 1, 2, 3, 4, 5, 6 and 7. Now if you count all together, this is 0, 1, 2, 3, 4, 5, 6 and 7. So total number will be 8. So that's the reason this is called as an octa or octal number system, and which will be having a base of 8 or radix 8. Since counting in octal involves 8 symbols, we can say that its base or radix is 8. The largest value of the digit in the octal system will be 7. Like we have started from 0 and the last will be 7. And after 7, it won't be 8. Isn't it? If you go with after 7, if you say that 8, 9, 10, so that are nothing but a decimal number. So after 7, the next number will be 1 and 0. So it will be 10. Then 11, 12, 13, 14, 15, 16, 17. And after 17, there is no 18. What will be the next number? 2, 2 and 0, then 20, then 21, and so on and so forth. So that's how the numbers goes in the case of octal number system. If you see the structure, so this is the radix point, then, and this is the least significant digit. Again, here it is called as a digit. and this is most significant digit. So because it is in an octal, so this will be, the positional weights will be 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, 8 to the power of 3. And here in the case of least significant digit, 8 to the power of -1, 8 to the power of -2, and 8 to the power of -3, and so on. This is the structure of octal number system. Since its base is 8, that is nothing but 2 to the power of 3. Every 3-bit group of binary can be represented by an octal digit. So this we have to remember when we convert a binary number into an octal number. So what simply we can do that every 3 from the least significant digit, if you move on, so we will make 3 binary numbers into a one group, and then we can easily convert a binary number into an octal number system. An octal number is thus 1/3 the length of the corresponding binary number, because we are dividing it by 3 groups. So it is nothing but the 1/3 the length of the corresponding binary number. Now please have a look onto this. So this is a decimal number system, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 13 they have given. Okay, and this is the equivalent of the decimal number system called binary numbers, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and all this up to 1, 1, 0, 1. Done. And these are the octal number system. So octal number system, how it goes, like 0, 1, 2, 3, 4, 5, 6, 7, and after 7 I told you it will be 10. 1 and 0, 10, 10, 11, 12, 13, 14, 15, after 15, 16, then 17. After 17, then it will come like, after 17, what will be the number? After 17, it will become like 20, 20, then 21, 22, 23, and so on and so forth. The last number system called as an hexadecimal number system. Now, binary numbers are long. These numbers are fine for machines, but are too lengthy to be handled by human beings. So there is a need to represent the binary numbers concisely. So that's the only reason we have this hexa number system, because we cannot write a huge binary bit numbers of 32 bits and larger than 32 bits. So instead of that, we can convert and put it into the hexadecimal number system. One number system developed with this objective is called hexadecimal number system, or basically it's called as a hex. So hex number system is a positional weighted system. It contains 16 unique symbols. Hexa itself is a 16. So what are the numbers it contains? What are the symbols? We can say that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9 it is A, B, C, D, E, and F. So altogether, if you count all the numbers, 16 symbols, this shows that it have a base of 16. Please don't get confused. See, octal number after 7 will get 10. But here after 7 we got it 8 and 9. In the case of decimal number system, after 9 will get 10. But here after 9 it is A, B, C, D, E, and F. Got it? Let's see the structure for the hexadecimal system. This is the radix point, and these are the hexa number systems: H0, H1, H2, H3, H-1, H-2. This is least significant digit, and this is most significant digit, because it have the base of 16. So this will be 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. In the case of this, 16 to the power of -1 and 16 to the power of -2. So this is the structure for the hexadecimal number system. Now since its base is 16, it means 2 to the power of 4. So every 4-bit group of binary can be represented by an hexadigit. So if you have 8, I say 4, or I say 2 nibbles. 2 nibbles is nothing but 8 bits. Then So we can make it into the form of 4-bit group and straight away convert into the hexadigit. An hexa number is thus 1/4 the length of the corresponding binary number, whereas in the case of octa number it was 1/3, because every 3 digits we have made one pair. Here every 4-bit group are made as in one pair. The hexa system is particularly useful for human communication with computer. Now, again, we are comparing the decimal, binary, and hexa. We have not shown here the octa. So just see that these are the plain decimal number. This we have already studied the binary number, and this is the hexa number. So 0, 1, 2, 3, 4, 5, 6, 7, up to 9 it will be 8 and 9. And after 9 it is A, B, C, D, E, F. So if I ask what is the equivalent of 111 binary number, so the equivalent in the form of hexa is F. So 15 is the decimal number, 15's binary equivalent is 1111, and 15th decimal number equivalent hexa is F. Now we have the conversion between all these 4 number system. Decimal we have seen, binary we have seen, octa we have seen, and hexa. So if you see this arrow mark, so we will be having a conversion between decimal to binary, and again binary to decimal, decimal to hexa, hexa to decimal, then binary to hexa, hexa to binary, octa to decimal, decimal to octa, octa to hexa, hexa to octa. All this kind of combination we will see into the next slide. Let us understand first how the decimal numbers are converted into binary. Because if you use a calculator or any digital gadgets, and if you do a mathematics onto that, and if I want to do a mathematics, say 2 plus 2, so I just key in 2 number and then the arithmetic symbol plus and then again 2 and then again, unless I show the 2 is equal to, it won't give a resultant answer like 4. But on the back end, for any electronic gadget, that decimal number is not understood by any electronic machine. That should be converted into binary. So on the back end, every decimal number is converted into binary. The arithmetic takes place into the form of binary only. It will get some certain answer, and on the display back to our calculator or monitor, it will show into the form of decimal. So how these decimals are converted to binary and binary are converted to decimal? Let's see this. What is the procedure? The procedure is divide the decimal number by the base 2, noting the remainder, continue to divide the quotient by 2 until there is nothing left, keeping the track of the remainders from each step. List the remainder values in reverse order to find the numbers binary equivalent. So this is the procedure. Let's take an example for this. So let's have the number called 105, which should be converted into binary. So what we need to do, divide it by 2. So we have divided it. So it is 52 are 1 is a remainder. Again 52 should be divided by 2, 26, 0 is a remainder. Again divided by 2, 13, 0. Again 6. I hope you can see this. 2 6 are 12, 1 is the remainder. Again divided by 2, so 2 3 are 6, 0 is the remainder. Then you got it in 1 and 1. So again if you divide it, 2 zeros are 0, so the remainder will be 1. So how we have to collect this answer from most significant bit to least significant bit. So to collect the answer, it is 1 1 0 1 0 0 1. So this is how the conversion of a decimal number, a whole number 105 with a base of 10, because this shows that because it is a base of 10, this is the decimal number. So 105 decimal number is converted into a binary form which is having a base of 2. So 1101 001. Now, if you want to have the conversion of decimal number into the binary number, but we have a fractional number system. That was a whole number and this is a fractional number. Then what we have to do? Multiply the given fractional number by base 2. Earlier what we did, we have divided it. We have divided it by 2. Here what we are doing, we are multiplying the given fractional number by the base 2. Record the carry generated in this multiplication as most significant bit. Multiply only the fractional number of the product in step 2 by 2 and record the carry as the next bit to most significant bit. Repeat the steps 2 and 3 up to 5 bits. That is enough. The last carry will represent the least significant bit of equivalent binary number. Let's see the example. If you see the example, it will be easy to understand. So we have converting 0.42 decimal number into its equivalent binary number. So what we need to do? We need to multiply by 2. So we have multiplied by 2. So how much is the answer? 0.84. This reminder we have to collect onto the right hand side. Now next, again, 0.84 should be multiplied by 2. It is 1.68. So 1 should be taken onto this side. And only again 0.68. Next time we don't take the 1.68. We just have to take 0.68. So 0.68 into 2, 1.36. 1 is taken over here. 0.36 into 2, 0.72. And 0.72 into 4, 1.44. So up to 5 bits it is enough. Now, how the collection of the answer is taken place from the most significant bit to the least significant bit. So this is the answer. So 0.42 decimal number, its equivalent into the binary is what? 0.0110 and 1. So this is an equivalent of a fractional number, fractional decimal number. Now the conversion between the decimal number system to octa number system. What is the procedure? Divide the decimal number by the base 8, noting the remainder. Same way, decimal to binary we have divided it by 2. Here decimal to octa we are dividing it by 8 and noting down the remainder. Continue to divide the quotient by 8 until there is nothing left, keeping the track of the remainders from each step. List the remainder value in the reverse order to find the number's octal equivalent. It is as simple as what we did in the case of decimal to binary. So convert, let us an example as 204 decimal number to its equivalent octa number. So divide by 8, it is 25. What is the remainder? Here you can see very clearly 825. If you do it, then the 4 is the remainder. We just collected 4 onto this particular right side. Again, this 25 quotient we have to take here, and again it is divided by 8. So 8 3s are 24. 1 is the remainder. Again, this 3 is divided by 8. So if you take the zeros up, then this comes as 3. So how the collection of the answer is done? From the main scale, from lower to upper. From lower to upper. So what is the answer for 204 decimal number? It is 314 with a base of 8. So this is not a decimal. Please, if you don't put a base of 2, 10, 8, 16, you will be messed up. So to identify it, to represent it, saying that it is an octa number system, there should be a base very clearly written. So 204 base 10 is converted into 314 octa number. If you have a fraction